Landauer's principle states that any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computation paths, must be accompanied by a corresponding entropy increase. And this has come to be seen as a fundamental limit to the efficiency of computation. Claude Shannon, the father of information theory, was deeply inspired by the close connection between entropy and information. He defined a new type of entropy, Shannon entropy. It can be interpreted as the amount of previously hidden information that can potentially be revealed by the observation of a random event. In a sense, it's a measure of the uncertainty of the event. The more uncertain or more unusual an event, the more revealing it is than a more predictable event. So for example, the roll of a die has more entropy than the flip of a coin. There are more potential outcomes in the former, so more uncertainty has been eliminated when the die is cast. Shannon used the term entropy for this measure because his formula was almost identical to the formula for thermodynamic entropy. Just multiply by the Boltzmann constant to get the latter. If you take all possible results of the die roll to be equally likely, then Shannon's formula looks just like the Boltzmann equation. This isn't a coincidence. In fact, Shannon entropy is, in a sense, just a generalization of thermodynamic entropy. The former describes the amount of hidden information in any system. The latter applies specifically to thermodynamic systems. And there's a third, perhaps even more fundamental type of entropy. That's quantum entropy, also known as von Neumann entropy. It describes the hidden information in quantum systems, but more accurately, it's a measure of the entanglement within quantum systems. In fact, the evolution of quantum entanglement may be the ultimate source of entropy, the second law, the limits of information processing, and even the arrow of time. We'll get tangled up in all of that in an upcoming episode of Space-Time. Entropy is surely one of the most perplexing concepts in physics. It's variously described as a measure of a system's disorder, or as the amount of useful work that you can get from a system, or as the information hidden by a system. Despite the seeming ambiguity in its definition, many physicists hold entropy to be behind one of the most fundamental laws in all of physics: information and entropy. It was Claude Shannon who founded the field of information theory and also invented the entropy of information, Shannon entropy. Shannon entropy can be thought of as the amount of hidden information in a system, or more precisely, the amount of information we can hope to gain by making a measurement of the system. If all the particles are bunched up in the corner, then measuring their exact positions gets you some information, but if you measure the positions when they're spread through the room, you increase your information by a lot more. Another way to think about Shannon entropy is in terms of events. The more possible outcomes of an event, the more entropy the event has. For example, a flipped coin is a low Shannon entropy event because it only has two outcomes, while flipping 1,000,000 coins is a high entropy event. Shannon entropy is actually more fundamental than thermodynamic entropy in that it is a generalization of the more familiar entropy. It applies to any system of information and any type of action that reveals that information. When he first came up with this theory though, Shannon didn't fully realize its importance. As the perhaps apocryphal origin story goes, he only started calling his invention entropy after talking to the great Hungarian mathematician and physicist John von Neumann. Supposedly, von Neumann said that he should call it entropy for two reasons. One, it looks exactly like the equation for thermodynamic entropy, and two, nobody knows what entropy is, so nobody would argue with him. Von Neumann had already invented his own brand of entropy, von Neumann entropy. It's the entropy of quantum systems. And because everything else is made of quantum systems, it may be the most fundamental definition of entropy. Even Shannon entropy is just a special case of von Neumann entropy. At least, so says von Neumann himself. The concept of von Neumann entropy is at least incredibly powerful. It's at the heart of quantum information theory, enabling us to calculate how much quantum information is contained in a system, and it can also be used to determine how many bits of classical information we can get out of the system when we make a measurement.